This question is expand opcode technique question. Just see the question. In that question, a processor has 64 registers, uses 16-bit instruction format. Instruction format given 16-bit. Processor contains 64 registers. Okay. It has two types of instructions denoted as I-type and R-type. Each I-type instruction contain opcode, register address and 4-bit immediate field. And each R-type instruction contain opcode and 2 register addresses. If there are 8 different I-type opcodes, then maximum number of R-type opcodes are. So we need to find out the R-type instructions in the system. Okay students, this is the given question information. Now we are going to apply the expand opcode technique to solve the question. Okay, so given data is instruction size is equal to 16-bit given. Instruction formats equal to I-type format and R-type format. Two types of formats given. Okay, different formats, but size of the instruction is fixed. So fixed length instructions uses the different formats. Fixed length instruction uses the different formats. Compulsory requires the expand opcode technique. So expand opcode technique is used to implement the different instruction formats on a fixed length instructions. So instruction length is fixed, formats are different. Compulsory we are using the expand opcode technique to design the different formats. Alright. What is the I-type instruction format? I-type instruction format is opcode, register address and immediate constant. This is given. 16-bit instruction it is. Immediate constant is 4-bit, they mentioned in the question. Number of registers are 64, that means 6-bit address. So remaining 6-bit is the opcode. Now R-type. R-type instruction format is opcode, 2 register operands, register, register. Okay, so this is also 16-bit instruction. Register address 64 registers, therefore 6-bit address. 6-bit, 6-bit. Rest of bits are opcode bits. Alright. So I-type format, R-type format, both are identified according to the given question information. Later, we are going to identify the opcode size. I-type instruction opcode is 6-bit, R-type instruction opcode is 4-bit. So smallest opcode is called as the primitive instruction. Largest opcode is called as the derived instruction. So here R-type is the primitive. R-type is the primitive and I-type is the derived. So first we need to design the R-type. Later, identify the free opcodes. Use them to design the I-type. Okay, first design the primitive instructions, identify the free space. Later, use the free space to design the derived instructions. That is the expand opcode technique procedure. Clear? Alright. So now here, what is present? I-type and R-type. R-type is the primitive, I-type is the derived. So in this design, we need to take the common parameter. Primitive, derived. Common parameter is opcode, opcode. Okay, and remaining register. Here register and immediate. See this, register common, so take as it is. Next, in the primitive you have a register, but in the derived you have a immediate. So these names are not common. When names are not common, we are taking the commonality in terms of the bits. So here 6 bit, from the 6 bits taking 4 bits for immediate and remaining 2 bits are merging with the free opcode. When 2 bits are merging with 4 bit free opcode, we get the 6 bit derived opcode. This is expand opcode technique. So follow this procedure to solve the question. Alright. So first what we are going to do? We are going to take the primitive format. Apply the steps. Step 1. Primitive format. Primitive format is opcode, register and register. This is primitive format. Size of the opcode is 4 bit, register 6 bit, again 6 bit. Okay, next. Second is number of operations possible is equal to 2 power opcode, that is 16. 2 power opcode, 2 power 4, that is 16. So 16 R-type instructions are possible. Okay, alright. Next, number of free opcodes. Third one, number of free opcodes. After R-type instructions. Number of free opcodes after R-type instructions, that is total number of instructions minus how many R-type instructions are present. In this question, R-type instructions are not given. We need to find out that. Then assume X R-type instructions are existed. Then find out the X value, that is the answer. So total number of opcodes minus X. X is the existed R-type instructions. Next, fourth point, number of I-address instructions, I-type instructions possible is equal to number of I-type instructions possible equal to free opcodes into 2 to the power of how many address bits are merging? 2 address bits are merging. Clear na? 6 bit register address. From the 6 bit, 4 bits are used for immediate. Remaining 2 bits are merging with opcode. So 2 power 2. Already in the question, they given the number of I-type opcodes. 8 I-type opcodes are already given. So here 8 equal to 16 minus X into 2 power 2, that is 4. Correct? So compute this. Calculate, simplify the equation. 16 into 4, that is 64 minus 4x. Okay, 4x is equal to 64 minus 8. So 4x is equal to 56, right? So x equal to 56 divided by 4. This is equal to 14. Okay, students. So how many R-type instructions possible? So here X is the number of R-type instructions existed. Now we find out the X value. X value equal to 14. So 14 R-type instructions are possible in the system. Okay. After implementation of 14 R-type instructions, we are going to design 8 I-type instructions. So I type instruction is a derived instruction, R type instruction is a primitive instruction. So here derived instructions are already given, we identified the primitive instructions. How many primitive instructions are existed in the system? Answer is 14. I hope you understand the solution. Is it clear? So with respect to this question, answer is 14. 1, 4. Answer is 14. Okay students, this is the solution. I am just showing you the total solution. Yes. Number of R-type instructions possible in the computer is 14. Clear? I hope you understand. Very good. In the question, 5-stage RISC instruction pipeline given, which is operating with 2 GHz clock frequency. So, first we need to identify the cycle time. So here 2 GHz clock frequency processor given that has a 5-stage RISC instruction pipeline. Therefore, cycle time of processor is equal to 1 by 2 GHz seconds. Okay, so this is equal to 0.5 nanoseconds. So cycle time of the processor is 0.5 nanoseconds. Okay, all right. Here processor has the 5-stage RISC instruction pipeline having a base CPI, matlab cycle per instruction of 1. So CPI of pipeline is always 1. That is also mentioned in the question. Without any pipeline hazards, there is no extra stalls or there is no extra cycles in the pipeline. Okay, CPI is equal to 1 as a ideal CPI. Okay. For a given program P, there is a program P that has 30% branch instructions. Program contain 30% branch instructions. Control hazards incur 2 cycle stall. That means branch instructions creates 2 stalls. That means branch penalty is equal to 2. So 2 stall cycles are created in the pipeline due to a branch instruction that is given. Okay, for every branch 2 stalls present. Okay. A new version of processor X2. There is the enhancement in the processor. Okay, new version of processor X2 operating at same clock. There is no difference in the cycle time. Clock frequency of the old processor, clock frequency of the enhanced processor, both are same. So old processor cycle time 0.5 nanosecond and new processor cycle time also 0.5 nanoseconds. Okay, but this new processor has an additional branch predictor. Okay, branch predictor is present in the enhanced system that completely eliminate stalls for correctly predicted branches. Okay, when the prediction is true, there is no stall. That is the meaning. When it is correctly predicted the branch, that completely eliminate the stalls. There is no stalls when the prediction is true. That is the meaning of this statement. There is neither any saving nor any additional stalls for wrong prediction. That means what? When the prediction is wrong, it does not create extra stalls. It does not reduces existing stalls. That means whatever the stalls present in the old processor due to the branch instruction, the same stalls are as it is present when the prediction is false. Okay, so those stalls are not increased, those stalls are not decreased in the new CPU when prediction is false. Got the point? When prediction is true, branch penalty 0. When prediction is false, branch penalty equal to old processor branch penalty. That is its meaning. Alright. There are no structural hazards and data hazards. There is no structural hazard, there is no data hazard for the old processor and also new processor. If the branch prediction unit has a prediction accuracy 80%, so 80% of predictions are true. That means 20% predictions are false in the new CPU. Okay, enhanced CPU. What is the speed up? Ask you to identify the speed up of a processor. Speed up of a enhanced processor over the old processor. This is the question. So question logic is this. Directly we can substitute the data in the formulas like this. Clock frequency 0.5 nanosecond. Already you know, given in the question. 2 gigahertz clock means 0.5 nanosecond. Alright. Now here old processor, that is denoted as a X1. X1 processor is there. Denotation is, they mention X1. Okay. Here there is a program which contain 30% branch instructions. So 70% are non-branch instructions. Non-branch instructions does not create any stalls. 0 stalls. Only branch instructions are creating the stalls. In the question, 2 stalls given. Branch instruction creates 2 stalls. This is the X1, old computer characteristics. Now calculate the execution time. So execution time of X1 is equal to 1 plus number of stalls per instruction into cycle time of the pipeline. This is a direct formula because pipeline is uniform delay pipeline. When they are not mentioned individual delays of a pipeline, we are treating pipeline as a uniform delay pipeline with a cycle time of 0.5 nanosecond. Now substitute the data. 1 plus 0.3 into 2. Okay. Multiply with 0.5 nanosecond. Do the calculations. What is the output? 0.8 nanoseconds. Is it right? So calculation is 0.8 nanoseconds. This is the execution time of a program in the old computer. Now we are executing the same program in the enhanced computer X2. Right, there is a program. In this program 30% are branch instructions. So 70% are non-branch instructions. Non-branch instruction creates 0 stalls. So in the branch instructions 80% branch predictions are true predictions. Then 20% branch predictions are false. Okay, true predictions 0 stalls, false predictions creating the stalls. Okay, old CPU stalls, new CPU stalls, same to same. Therefore substitute the data in the formula. Execution time of X2 equal to 1 plus number of stalls per instruction into cycle time. Okay, substitution 1 plus 0.3 into 0.2 into 2. These are the number of stalls per instruction into cycle time of the processor is 0.5 nanosecond. Do the calculations. This is 0.56 nanoseconds. Okay, students. So old CPU execution time, new CPU execution time calculated. Now we need to report the performance gain of an enhanced CPU. Performance gain of enhanced CPU, speed up S equal to execution time of old CPU by execution time of new CPU. 0.8 nanoseconds upon 0.56 nanosecond. Okay, substitute the data and compute the value. This is equal to 1.42. Speed up of the enhanced system is 1.42. Okay, students. Yeah, this is the question, numerical question. For this question, when we calculated the execution time of X1, that is old computer, that is 0.8 nanosecond, and execution time of enhanced computer, that is 0.56 nanosecond. After that, speed up value, performance gain of the system is 1.42. So answer is 1.42. Hope you understand the solution. Is it clear? All right. In the question, 4 KB byte addressable memory is realized by using the 4 1 KB memory blocks that is described in the question as a diagram. See that 4 KB byte addressable memory. Capacity of the memory is 4 KB. Configuration of the memory is byte addressable. Byte addressable memory means cell size equal to 8 bit. Okay, so 4 KB byte addressable memory is realized by using 4 1 KB memory blocks. So total 4 blocks are given with each block capacity of 1 KB described in the diagram. This is the first 1 KB block, second 1 KB block, third 1 KB block, fourth 1 KB block. So total 4 1 KB blocks are present in the diagram, which are used to describe the 4 KB byte addressable memory unit. Alright. Here 2 input address lines named as IA4, IA3. IA input address. Okay. IA3, IA4. 2 input address pins are connected to the decoder circuit. This decoder circuit is connected to the chip select logic of each memory block. Given in the question like this. IA3, IA4. That means input address 3, input address 4. These 2 address pins are acting as a chip select pins in this design. Here IA3, IA4 connected to the decoding circuit. From the decoding circuit, 4 output signals are coming. So each signal is connected to the respective memory block chip select logic. That is, Q0 is connected to the chip select logic of first 1 KB block. Q1 is connected to the chip select logic of second 1 KB block. Q2 is connected to the chip select logic of third 1 KB. Similarly, Q3 is connected to the chip select logic of fourth 1 KB block. Okay. Also, they given that chip select logic is active high. That means this chip select logic is enabled when the input is 1, active high. Alright. Now, input address lines IA4, IA3 are connected to the chip select port of these memory blocks, which I already explained, through the decoding circuit shown in the figure, right? The remaining 10 input address lines. Total 12 address lines because 4 KB. So 2 address lines are used as a chip select logic lines which are connected to the decoder circuit, and remaining 10 address lines from IA0 to IA11 are connected to the address port of these blocks. That means in the total 12 address lines, address line 3, address line 4 are used as a chip select lines, and rest of the address pins are used as the address bus or else addressing of the respective memory unit. Okay, alright. Chip select logic is active high. After reading that question, we realized this: A0, A1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Total we have a 12 address pins. In the 12 address pins, 2 pins are connected, A3, A4. These 2 pins are connected to the decoder. They are used as a chip select logic. Straight away, these are the chip select logic pins. Alright. 2 pins are having total 4 combinations. They are 0, 0, 0, 1, 1, 0 and 1, 1. So, when this status is 0, 0, when the A3 and A4 0, 0, then Q0 signal is generated from the decoder. So, when A3 and A4, A3 is connected to A0, A4 is connected to A1, LSB and MSB. So, when A3, A0 status 0, 0, then decoder output is Q0, 0, 1, decoder output is Q1, 1, 0, decoder output is Q2, 1, 1, decoder output is Q3. That is mentioned according to the diagram. Now, when the decoder output is Q0, then first 1 KB X1, that means X1 data will be activated, or else you can say first 1 KB block is activated. First 1 KB block is activated. Next, if it is a Q1 signal from the decoder circuit, second 1 KB block is activated. Okay, Q2, third 1 KB block is activated. Q3, fourth 1 KB block is activated. Like this, based on the status of A3 and A4 pins, chip select logic will be activated. Alright, fine. The remaining 10 address pins. What are the remaining 10 address pins? A0, A1, A2, A5, A6, A7, A8, A9, A10, A11. They are addressing the memory. Very nice. Now, the input memory address, this is the memory address, IA0 to IA11. This is the input memory address in decimal. For the starting locations are the address equal to 0. So, in every memory bank, starting address will be 0. That means cell 0, cell 0 and cell 0 and also cell 0. Got the point? Starting addresses of locations of each block indicates X1, X2, X3, X4. So, this is the X1. X1 indicates the starting address of first block. X2 indicates the starting address of second block. X3 starting address of third block. X4, starting address of fourth block. So starting address means address 0. Address 0 means cell 0. Okay. So cell 0 address is nothing but all zeros. Okay. They mentioned clearly address equal to 0. So starting address should be all zeros. So we need to activate the first cell from the first bank or else first block. First cell from the second block. First cell in the sense starting cell is nothing but a address 0. So I want the cell 0 accessibility from each bank or from each block. Okay. So what are the decimal addresses? They are giving the decimal address sequence. We need to find out the starting address of the first bank or first block, starting address of the second block, starting address of the third block, starting address of the fourth block. Very simple. Starting address is what? Here we are going to take all zeros, 0, 0, 0, again 0, 0, 0, 0, okay, and here also 0, 0, 0. Okay, if I take all zeros, this is the starting address. Starting address of what is this? First block. Then what is the hexadecimal? What is the decimal address of this? Decimal address of these 12 bits equal to 0. Alright. Next, starting address in the second block. 0, 0, 0, 0, 0, 0. Let me write 0, 0, 0, 0, 0, 0, 0. Next 0, 0, 0. What is the decimal value? Question is expecting the decimal value. So decimal value of this is 8. Okay, this is the 8 decimal value because this. When A3 and A4 status is 0, 1, decoder output is Q1. Q1 means second 1 KB block is activated. Alright, that is the starting address from the second memory block. Next, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. This is the starting address of the block 3. How we know it is a starting address of block 3? Because A3 and A4 status is 1, 0. A3, A4 status is 1, 0. Q2 is the output signal of decoder. Q2 output signal is connected to the chip select logic of third 1 KB unit. So from the third 1 KB unit, you can access the data. Okay. So now, what is the decimal number of this address? So decimal value of this address is 1, 2, 4, 8, 16. 16 is the answer. Right. Now starting address, last unit. Starting address means all zeros. If I put all zeros here, I3 and I4 status is 1, 1. I3, I4 status 1, 1 means decoder output is Q3. Q3 means fourth 1 KB block is activated. You know, Q3 connected to the chip select logic of fourth 1 KB block. So we are accessing the first cell, that means starting location from this fourth 1 KB block with this location or with this address sequence. Now find out the decimal value of this sequence. 1, 2, 4, 8, 16. This is equal to 16 plus 8, 24. So these are the address sequences in decimal. Address sequences in decimal to access the data from the 4 blocks with a starting address 0. You see this? This is the first 1 KB block starting address. This is the second 1 KB block starting address. This is the third 1 KB block starting address. This is the fourth 1 KB block starting address. So from each block we are going to access the data with starting address all zeros. Okay, so decimal number sequence with respect to those addresses are 0, 8, 16, 24. Okay, so in this question, if you see the options, okay, correct option matching is 0, 8, 16, 24, this one.